Guys, this is Dr. J here, and in this particular video we will talk about structure and stability of benzenes. So benzene has a chemical formula C6H6, and it is a cyclic compound. It is a cyclic compound. So if you think about it, it kind of looks like a cyclohexane, right? It kind of looks like cyclohexane, where you have a 6 carbon ring, and according to the formula, each carbon should also have a hydrogen. Each carbon should also have a hydrogen. And of course, each carbon should also have 4 bonds. So therefore, benzene is going to have 3 alternating double bonds. It is going to have 3 alternating double bonds in this ring structure. And of course, each carbon has a double bond. So the hybridization should be sp2. Okay, so in benzene, you have 6 equivalent carbons. Each carbon is sp2 hybridized, and each carbon has a double bond and 2 single bonds, of course, because of the hybridization. And also they have one hydrogen atom directly attached to each carbon. Okay, so this is how benzene look like. So if you take a look at the skeletal structure, it kind of looks like this. Okay, so this is the skeletal structure for benzene. All right, so that is the structure of benzene. But here's the thing. I mean, benzenes have alternating double bonds. So basically, from the alkene and alkane lessons, we already know that double bonds are shorter than single bonds, right? Double bonds are shorter than single bonds. So when writing benzene, we don't show that. Okay, so from our previous understanding, it should be like these: double bonds are shorter. I'm going to draw an exaggerated view of benzene. Single bonds are longer. Okay, so it should kind of look like this. Okay, double bonds are short, single bonds are long. But no, we don't draw like this when we are drawing benzene. Instead we are using a very symmetric hexagon ring, and there is a reason for that. Okay, there is a reason for that, and we will talk about it in more detail in the next couple of slides. And also, as you can see, benzene also has three double bonds, 3 alternating double bonds. So it should react like alkenes, right? So if you remember your alkene lesson, okay, let's take propene as an example. I mean, they easily react with molecules like bromine to give you addition products, right? To give you addition products. So here is the addition product. But if you try to do the same reaction for benzene, you will not get any products. You will not see this addition product. You will not see this particular addition product. So even though benzene kind of looks like an alkene with 3 double bonds, or a cyclic alkene with 3 double bonds, the reactivity is nowhere close to traditional alkenes. Okay, the reactivity is actually much less. If you want to react bromine with benzene, you will have to add an additional catalyst. Okay, so for alkenes we didn't use any catalyst, right? But for benzenes, even though it has 3 double bonds, you still have to use a catalyst like iron. Okay, and then the product that you get is not an addition product, because they are not losing any of the double bonds. Instead, they are replacing one of the hydrogens with bromine. So this is a substitution reaction. So you are not getting the traditional addition product in this reaction. Instead, you are getting a substitution product, and to get the substitution product, you also have to use a catalyst. So by now we know that these reactions are not very favorable, because you need to put a lot of work into it, and you have to use catalysts for this reaction. So the reactivity is much less when it comes to benzene. So in chemistry, reactivity and stability are opposite to each other. Reactivity and stability are inversely proportional to each other. So if reactivity is inversely proportional to stability, that means since benzene reactivity is low, okay, stability should be high, okay, and vice versa. All right, so for benzenes, since the reactivity of benzene is very low as compared to alkenes, stability of benzenes should be high, okay. So we will talk about the stability of benzenes in more detail in the next few slides. All right, so this is a diagram from your John McMurray textbook that we use in organic chemistry. Okay, so in here it compares the heats of hydrogenation, okay, as an indicator for stability. Okay, so you know cyclohexane is more stable as compared to cyclohexenes, right? So whenever you introduce double bonds, whenever you introduce double bonds, they are not as stable. Okay, so if you try to react these cyclohexenes with hydrogens, you will get back your cyclohexene. Okay, you will get back your cyclohexane. Okay, so cyclohexenes will basically react with hydrogen and give you cyclohexane. Okay, so this reaction is favorable. Why? Because it releases energy. Okay, so it's an exothermic reaction. Okay, exothermic reaction, and the product that you get is more stable. Okay, so if you have more double bonds, like 1,3 cyclohexadiene, it has two double bonds. So the heat it releases during hydrogenation is more, because this diene is more unstable as compared to cyclohexene. So technically, we expect benzene to be even more unstable. Why? Because it has one more double bond, right? So whenever you increase the number of double bonds, the molecule should decrease the stability, and therefore when you hydrogenate, when you try to react it with hydrogen to obtain cyclohexane, it releases energy and it becomes more stable. Okay, so but that is not the practical situation. We expect it to be releasing a lot of energy, but actually what we see is a lot less energy released during this hydrogenation reaction. During this hydrogenation reaction, we see around 150 degrees less energy release. That means as compared to the theoretical expectation of the stability, benzene is 150 kilojoules per mole more stable. Okay, benzene is actually more stable than the traditional three double bond cyclohexene expectation. Okay, so benzene is more stable. So benzene energy is at this point, okay, 150 kilojoules per mole less than the expected value. So now we know for sure, practical in this experiment, we know that we learned that, okay, benzene is actually more stable than regular alkenes. Okay, but why? The question is why. So in order to answer this, let's take a look at the structure of benzenes. Okay, let's take a look at the structure of benzenes. As you can understand, okay, benzene has 6 carbons and 6 hydrogens, and it has 3 alternating double bonds. It has 3 alternating double bonds. Okay, so the structure kind of looks like this, but of course they can have 2 resonance structures. Whenever you have alternating double bonds, we learned that you can switch locations, right? And then you can show a different resonance structure. Okay, so because of this, because of these 2 resonance structures, okay, here's the first resonance structure, here's the second resonance structure. Okay, they are always switching between the two because they are almost identical, right? They are identical, only difference is that their double bond location is changing all the time. Okay, they are flipping from one to another all the time. Because of that, on average, you can assume that these double bonds and single bonds are basically 1.5 bonds, 1.5 bonds, because they are always switching between a single bond and a double bond, and it is very fast. So you can assume that, okay, it is like having 1.5 bonds. So they are neither double bonds nor single bonds. They are in between. Okay, that is how you actually get a benzene. That is how you actually get a benzene with 6 identical bonds. Okay, 6 identical bonds. Even though we draw them as double bonds and single bonds, we know that they are always changing into the opposite kind or the other kind, and then at a given point of time they look like 1.5 bonds. Okay, and if you take a look at the bond lengths, these bond lengths actually is a prime evidence for that. So when you take a look at the carbon-carbon bond lengths, okay, it basically has around 139 picometer bond length, which is basically in between a single bond and a double bond length. Okay, so these experimental results actually provide evidence for these resonance structures. Okay, and also the electron densities. If you look at the electron density diagram, it has all 6 carbons with identical electron densities. No carbon has more electron density as compared to the other. Whenever you have a double bond, you expect certain carbons have higher electron densities, but no. Instead, all 6 carbons are equal. So basically, what we can assume in this case is that rather than having these double bonds and single bonds fixed to a certain location, these pi electrons on double bonds, okay, these pi electrons on double bonds are delocalized into the ring. So these pi electrons, each double bond is what? One sigma bond and one pi bond, right? So 2 electrons from each double bond, so you basically have 6 pi electrons, right? So all of these 6 pi electrons, rather than centered into just 3 double bonds, they are actually delocalized into all 6 carbons, so that all 6 carbons will be equal. So basically you can picture this as having 6 electrons flowing equally on all 6 carbons. Okay, flowing equally on all 6 carbons. Okay, so that is how you can picture this, because you already know that each carbon is sp3 hybridized, right? So if it is sp3 hybridized, you know that it has a double bond, a single bond, and a carbon hydrogen bond. Okay, so the bond angles are around 120 degrees, right? And then you have a p orbital perpendicular to the other 3 bonds, right? The double bond and the 2 single bonds. So this p orbital is perpendicular, and here is the sp3 hybridized carbon, sorry, sp2 hybridized carbon, and each carbon has this electron. So rather than making fixed double bonds with one carbon, they basically share all these 6 electrons in a ring current. Okay, so like a stream of electrons. So that is how this benzene electron density could be explained. And also this benzene has 6 sp2 hybridized carbons, and as you know, when you have sp2 hybridized carbons, each carbon has a trigonal planar structure, right? Each carbon has a trigonal planar structure, which means all 3 bonds are in the same plane. Okay, so therefore the structure of benzene is planar. That is important to remember. Structure of benzene is planar, and it is a hexagonal structure. All right, so that is the structure of benzene. And then also I mean in this slide it basically further explains what I just mentioned, so you can pause the video and read this slide if you have to, and if you have any questions. But basically the 3 double bonds that we have, okay, each double bond gives you 2 pi electrons. So basically you have 6 p electrons, or 6 pi electrons from the 3 double bonds, and they are delocalized between the 6 carbons. And basically your benzene ring is a planar structure, and p orbital is sitting on top and bottom of the benzene. So these 6 p orbitals are basically sharing all these pi electrons, and they are delocalized into these p orbitals. All right, and these pi electrons of course are moving freely, generating a ring current. All right, so resonance stability is already discussed in the previous slide. So rather than drawing these uh, resonance structures for benzene, we can have a hybrid structure for benzene. Okay, so basically in this hybrid structure, rather than drawing 3 pi bonds, we can draw a ring inside the hexagon. Okay, so this hybrid structure can also be used to represent benzene. Rather than drawing one of the two resonance structures, people tend to use this hybrid structure. Okay, and this basically hybrid structure, this ring means it has 6 pi electrons for benzene, and they are all equally delocalized between all 6 carbons. Alright, so this is the molecular orbital description for benzene. Okay, so you basically have 6p orbitals in the 6 carbons. Okay, and when you take a look at the molecular orbital diagram, as you can see, the 6 p orbitals will form 6 molecular orbitals. Okay, 3 bonding orbitals and 3 anti-bonding orbitals. But when you populate the orbitals, molecular orbitals, you will only populate the bonding orbitals, right? You will only populate the bonding orbitals. So basically the 3 bonding orbitals will contain all 6 pi electrons, and the anti-bonding orbitals will not have any pi electrons. Okay, all right, so this is the molecular orbital diagram for benzene, and it also shows you the stability of benzene. All right, so in the next slide I have a worked example. Okay, I actually really want you to try this. Okay, if you understand the benzene structure, you should be able to do this without my help. Okay, so in here I want you to consider pyridine. Okay, we already learned benzene. I want you to consider pyridine, which is C5H5N. So if you look at the difference between the two, in pyridine, you basically replace a carbon and a hydrogen. You replace a carbon and a hydrogen with a nitrogen. That is the difference. Okay, that is the difference. So for pyridine, you replace 1 carbon and 1 hydrogen with a nitrogen. So in this, according to this worked example, pyridine is also a flat hexagonal molecule. It is also a flat hexagonal molecule with 120 bond angle. That means the sp2 hybridized, right? It is also sp2 hybridized, and basically it behaves like benzene. Okay, so I want you to draw a picture of the pi orbitals of pyridine and explain it. See if you could do it. You might want to pause the video now. All right, so as you know, in this drawing I have shown you the benzene structure. Okay, so if you basically take one of these carbons, okay, if you take one of these carbons, it kind of looks like this, right? Each carbon is sp2 hybridized. It is sp2 hybridized. That means you have a double bond and 2 single bonds, and then of course the bond angle is around 120 degrees. The bond angle is around 120 degrees, and then also each carbon has a p orbital which is perpendicular to the 3 bonds. Okay, it is perpendicular to the 3 bonds. So this is how each of these carbons look like. So in this example, what you do is you are replacing a carbon and a hydrogen. You are replacing a carbon and a hydrogen with a nitrogen. And can you do that? Okay, can you do that? So let's take a look at it. Okay, so if you take a look at carbon, okay, carbon basically is from group number 4a, so it only has 4 valence electrons. Old story, right? But nitrogen has 5 valence electrons, which means it already has a lone pair. Right? So basically lone pair is like what? Lone pair is like a single bond without anything attached, right? So basically this lone pair can easily replace the carbon and hydrogen bond. Okay, this lone pair can easily replace the carbon hydrogen bond. So basically you take the same old benzene and you replace this carbon hydrogen with nitrogen, and of course the lone pair will take place of the carbon hydrogen bond, and of course the the p orbital will remain intact. Okay, the p orbital will remain intact. Okay, so let me replace this with carbon and hydrogen just to be clear. Okay, so I'm replacing the carbon and hydrogen with the nitrogen, but since it already has a lone pair, this lone pair will replace the carbon hydrogen bond, and then you will use 2 electrons to form the double bond. These two can be used to form the double bond, and this could be used to form the single bond. Okay, so this is the single bond, this is the double bond. Okay, are we clear? So let's go back to our presentation, and if you take a look at the answer, okay, in here you will basically have the exact same benzene ring, but the one carbon and hydrogen could be easily replaced by nitrogen. Okay, and the nitrogen lone pair will be perpendicular to the p electron cloud. It is not interfering with the p electron cloud. Okay, why? Because this is a part of sp2 hybridization. Okay, so this is perpendicular, so it is basically just like a carbon hydrogen bond. Okay, and here are the written explanations if you want to pause the video and take a look at it. Okay, but I already explained them to you in more detail. Alright guys, with that I'm going to conclude this video. Okay, and I will see you guys in the next video. Alright, you guys have a good one. Take care.